Have you ever seen the gigantic scale at which Coca-Cola gets produced? Producing millions of bottles per day, there's a massive difference between how they make normal bottles, their cherry flavor, and zero variant. Today, we're investigating how they make all of these types of Coca-Cola, revealing their secret method for doing it at such an unbelievable speed. In the high output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, can production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counterpressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for bricks levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine. Syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins, not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high-shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup-to-water ratio down to 0.1% so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, Every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high Brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 grallis of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, Paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +/- 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Celsius to 98 degrees Celsius. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees Celsius. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives. Remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate enrobing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree Kelvin. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees Celsius. To create multiple flavor variants, the unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the weigh-filler interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle, verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk. Sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar-glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees C. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film, printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill-seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing Nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored Nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. a fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 degrees to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills two parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of two flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed, and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotostator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees Celsius over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. Excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100-200 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat-sealed along the underside, and crimp-sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector, calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons, automatically erected from flat blanks. Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 °C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, Steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Pre-formed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor, aligned with the mold indexing system, dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping infeed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with tool-less part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process. Sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coated one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single-file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second, over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent, followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0.15 mm. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 mm. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle to print timing, is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once, and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces: syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a de-aeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on-site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, Every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. KFC's fried chicken may be iconic for its secret blend of 11 herbs and spices, but the factory process behind every crispy, golden piece is built on something far less mysterious: precise engineering, timed workflow, and ruthless consistency. Behind every bucket of original recipe is a production line designed to turn raw chicken into seasoned, breaded, and pressure-fried perfection on a massive global scale. Millions of pieces per day across thousands of locations, all starting in high-throughput poultry processing facilities. The process begins at the poultry plant, long before any chicken sees a fryer. KFC doesn't raise its own chickens. Instead, it partners with large-scale poultry suppliers who specialize in high-efficiency, vertically integrated operations. These facilities process thousands of birds per hour using lines that are fully automated and regulated to deliver uniform size, weight, and quality. Once chickens arrive at the facility, they're stunned and humanely slaughtered, then passed through defeathering machines. The birds are washed, eviscerated, and chilled in cold water or air-chilling tunnels, depending on the region and regulatory requirements. From here, they move to automated cutting lines, where high-speed blades segment each bird into standardized cuts: drumsticks, thighs, wings, and breasts, with specific sizing tolerances so each piece will cook evenly during pressure frying. Every piece is trimmed and inspected, then sent through water jet portioning systems, lasers, and nozzles that precisely cut meat based on optical sizing. Pieces are sorted by weight to ensure uniform cook times, then chilled to below 40 degrees Fahrenheit and packed in vacuum-sealed bags. These raw chicken portions are shipped to regional KFC prep centers or directly to KFC kitchens, depending on location. At centralized KFC prep facilities, often located near urban hubs or distribution centers, the real transformation begins. Here, each piece of raw chicken is thawed, if frozen, washed, and carefully inspected again. Workers wear full food-safe suits, gloves, and hairnets, operating under strict HACCP protocols to avoid cross-contamination. Every batch is handled in cold prep rooms, where the air is chilled and filtered to keep bacterial growth to a minimum. Then comes the marination phase, a foundational step in the flavor and texture of KFC's chicken. Each piece is soaked in a liquid brine, typically a mix of water, salt, phosphate, and other flavor-carrying compounds. The phosphate acts as a moisture-retaining agent, helping the chicken stay juicy through frying. This brine is vacuum tumbled into the meat using large rotating drums, which massage the liquid deep into the muscle fibers over the course of 30 to 60 minutes. Every load is weighed before and after to ensure absorption is within spec. Next comes seasoning. Contrary to myth, the famous 11 herbs and spices are not mixed at every location. Instead, the spice blend is produced at a secure, centralized facility where the exact combination is pre-measured and packed into coated, tamper-proof bags. These bags are shipped to prep centers or stores where they're added directly to flour for the breading process. Only a few people in the company know the full recipe, and the factory itself is designed to prevent accidental or deliberate disclosure. Even the workers handling the blend often don't know what's in it. In the prep facility, seasoned breading stations are set up in long rows where chicken moves through the legendary hand breading process. Each piece is dredged in seasoned flour, then placed in a shallow basket where it's pressed into the flour with a very specific folding and compression motion. This step, called the 7-10-7 method, is taught to every KFC cook and replicated in prep facilities worldwide. It's part of what gives KFC chicken its craggy, crunchy, uneven texture. The breaded pieces are then loaded onto trays and either flash chilled for shipment or sent directly to in-house kitchens for frying. In some markets, partially cooked chicken is sent to stores to shorten fry times during service rushes. But in most regions, frying is done fresh in-store, using the same tightly controlled procedure. In KFC restaurants, pressure fryers are the beating heart of the operation. These aren't just deep fryers, they're sealed, industrial pressure cookers that fry chicken under high pressure and temperature. The typical fryer operates at around 350 degrees Fahrenheit under 12 psi, allowing the chicken to cook faster and retain more moisture than open frying. The result? A crisp exterior with a tender, juicy interior, cooked in about 10 minutes per batch. Each piece is loaded into a wire basket or chicken clamshell, arranged in a way that ensures even oil flow. The basket is locked into the fryer, the lid is sealed, and the cook cycle begins. Once complete, the fryer releases pressure and the basket is lifted. Every batch is placed on a draining rack, where oil drips off and the crust sets. From there, chicken is either held in warming cabinets kept at a specific humidity and temperature, or served immediately, depending on demand. Quality checks are frequent. Staff use thermometers to confirm internal temperatures, visual checks to verify color and breading coverage, and taste tests to ensure consistency. Any batch that sits too long is discarded to maintain quality standards. Back in the prep centers, not all chicken ends up as original recipe. KFC also produces extra crispy, spicy, and grilled varieties, each requiring slightly different breading and cooking profiles. Extra crispy chicken, for instance, goes through a double breading process with a coarser flour blend and is fried in open fryers, not pressure ones. The breading station must be cleaned and reset between batches to avoid cross-contamination between flavors. Meanwhile, grilled chicken is seasoned differently, rubbed with a dry spice mix and roasted in combi ovens, not fried at all. These ovens use steam and convection to cook the meat evenly while keeping it juicy. The flavor is more subdued, but the factory process behind it is just as strict, with marination and seasoning steps done under cold room conditions before transport. Throughout the entire system, data is king. Every batch of chicken, from farm to fryer, is logged with timestamps, location codes, and supplier data. Digital systems track everything from fryer oil turnover rates to breading mix usage, ensuring that no store deviates from standard operating procedures. Even the oil itself is filtered between batches and replaced on a tightly controlled schedule. Sensors monitor fryers for temperature drift and alert staff if anything strays outside of spec. Sanitation is constant. Between batches, breading stations are cleaned, gloves are changed, and utensils are sanitized. The entire prep room in a factory is stripped down at the end of each shift and pressure washed with food-grade disinfectants. Air in the facility is filtered and recirculated to control temperature and humidity. Workers follow strict entry protocols, passing through air curtains and sanitizing stations before handling any food. And while the public rarely sees it, KFC's factory network is global but highly localized. Facilities are located close to supply chains and restaurants, so that chicken can go from bird to bucket in as little as 48 hours. Some regions operate their own prep hubs, while others rely entirely on in-store breading. Regardless of setup, the steps, the cuts, the brining, the seasoning, the breading method, the pressure fry cycle are replicated with uncanny consistency, batch after batch, store after store. So even though the end product might look simple, a crispy thigh, a golden drumstick, a perfectly breaded breast, it's the result of a highly engineered process that controls every variable, from feedlot to fryer. Every bite of KFC chicken is a small miracle of industrial food science wrapped in proprietary seasoning and delivered at a speed that only automation, logistics, and relentless procedural training can provide. McDonald's burgers may feel like fast food, but behind each patty is a global factory system built for scale, safety, and precision engineering. Millions of burgers are served every single day, and nearly all of them can be traced back to a production process that transforms whole sides of beef into standardized, flash-frozen patties in minutes. At the factory level, making a McDonald's burger isn't about cooking. It's about control of sourcing, fat content, texture, shape, temperature, and microbiological safety. It's meat processing at the scale of aerospace manufacturing. It all starts with the raw material, beef trimmings. McDonald's doesn't use mysterious filler meat or pink slime in its regular burgers. It uses 100% beef, mostly lean trimmings left over after the most valuable cuts, like steaks and roasts, are removed from the carcass. These trimmings arrive at the processing facility in large vacuum-sealed containers, chilled and tracked by batch number and origin. Every shipment is tested before it's even unloaded, scanned for temperature consistency and contamination. Inside the facility, which is refrigerated from wall to wall, the beef moves quickly from receiving to grinding, but not before it's blended. Each patty, whether for a Big Mac, a quarter pounder, or a basic hamburger, has a target fat ratio, typically around 20% fat to 80% lean. Because beef trimmings vary in fat content depending on where they come from on the cow, the factory uses a fat analysis system to create the perfect blend. Optical scanners and near-infrared sensors analyze the fat levels of incoming meat in real time. The system then pulls from different bins of lean and fatty meat and blends them together, like dialing in a recipe by percentage. This blended beef goes into massive grinders, long stainless steel augers that push the meat through ultra-sharp blades, creating a uniform texture. The meat is not overly ground. The goal is to keep the bite structure intact so the patty doesn't become mushy. From here, the ground beef flows into a forming machine, a high-pressure system that presses it into exact size patties using precision molds. Each mold is designed to create uniform diameter, thickness, and weight. For example, a quarter pounder patty is exactly 4 ounces before cooking, while a standard hamburger patty is closer to 1.6 ounces. The forming system presses the meat into a specific density to account for shrinkage on the grill, ensuring that even after cooking, it fits the bun perfectly. But here's where the engineering gets fascinating. McDonald's patties are never seasoned, never pre-cooked, and never touched by human hands once they enter the forming line. The formed patties drop directly onto a freezing conveyor belt, where they're flash frozen at 40 degrees Fahrenheit within minutes. This rapid freezing is crucial. It locks in moisture, halts microbial activity, and stabilizes the patty's shape. The faster the freeze, the smaller the ice crystals, which means better texture when cooked later. As patties move through the spiral freezer, they are spaced evenly and continuously monitored by infrared temperature sensors and metal detectors. Any patty that's not perfectly shaped, underweight, or too warm is rejected automatically and diverted for reprocessing. Frozen patties are then stacked into rows by robotic arms and inserted into cartons. These boxes are barcoded, batch-coded, and sealed, then loaded onto pallets for deep frozen storage at 20 degrees Fahrenheit, ready to be shipped to McDonald's distribution centers. Throughout this process, every movement is tracked. Each patty has a data trail that includes time of production, meat origin, grinder settings, fat ratio, freezing time, and packaging line number. Back at the restaurant level, things are equally standardized. Frozen patties arrive in boxes labeled by product type: hamburger, quarter pounder, Big Mac, and are stored in walk-in freezers. When it's time to cook, grill operators pull the exact number of frozen patties needed and place them directly onto clamshell grills. No thawing required. These grills, automated and heated on both the top and bottom, close over the patties and apply uniform pressure and heat. A standard hamburger patty cooks in about 42 seconds. A quarter pounder, which is made from fresh, never frozen beef in some markets like the US takes slightly longer and is grilled manually to order to preserve texture. The grills are calibrated down to the degree and the cooking time is preset. There's no guesswork, only automation. As the burgers cook, excess fat and moisture drain away through grooves in the grill, while sensors monitor temperature to ensure food safety. Once finished, patties are lifted by the operator and placed into holding trays, where they're kept warm for a maximum of 10 to 15 minutes before being discarded if not served. Another strict quality control rule. No seasoning is added during production. Only salt and pepper are applied after grilling, just before the burger is assembled. This ensures the seasoning is fresh and that the meat surface stays dry enough to achieve the Maillard reaction, giving the patty a browned, flavorful crust. While the patty is the star, the buns are also factory made for exact compatibility. Hamburger buns are baked off-site in high-speed bakeries, cooled, sliced, and flash frozen to lock in moisture. They're toasted at the restaurant on dual contact toasters that heat them to 500 degrees Fahrenheit for just a few seconds, creating a warm surface that resists sogginess and clings to condiments. Each component, from the beef to the bun, is timed, measured, and assembled within seconds at the line. An average McDonald's kitchen can assemble hundreds of burgers per hour, all with patties that are nearly indistinguishable in shape, taste, and texture, because the factories that produce them are engineered to eliminate variation. Sanitation in the patty factory is non-stop. Every surface is stainless steel. Workers wear full body protective gear, pass through air showers, and sanitize hands and boots before entering food zones. All grinders, forming machines, belts, and hoppers are cleaned in place using high-pressure foam and steam sanitation systems. Air is HEPA filtered to prevent microbial spread, and environmental swabs are taken daily for bacterial testing. No part of the system operates without data. Every piece of equipment, from the meat blenders to the freezers, feeds information into a central dashboard monitored by food engineers and safety personnel. If temperatures shift, blade pressure fluctuates, or a batch goes even slightly out of spec, alerts are sent immediately, and the line can be stopped in seconds. Even the sustainability goals are tracked here. Many factories have adopted water recycling, energy-efficient freezers, and methane recovery from meat waste. Trimmings and rejected patties are rendered and repurposed, not wasted. At full capacity, a McDonald's beef patty plant can produce over 2 million patties per day. And despite that staggering number, the quality targets are tighter than many artisanal kitchens. Each burger you unwrap may feel mass-produced, and it is, but it's made in a system where every variable is measured, every motion is repeatable, and the only acceptable outcome is a patty that cooks the same way, looks the same way, and tastes the same way, anywhere in the world. So while the end product may feel fast and disposable, the factory behind every McDonald's burger is anything but. It's a cold, stainless steel symphony of grinding, forming, freezing, and packaging. A controlled ecosystem designed to deliver something incredibly consistent at a scale few other food systems can match. Subway may be known for its made-to-order sandwiches, but the illusion of freshness at the counter is only possible because of a vast, behind-the-scenes production system. One that begins in massive factories designed to produce pre-portioned, pre-baked, and ready-to-build components for every sandwich on the menu. From the foot-long bread to the uniform stacks of meats and sliced vegetables, nearly everything is prepped in specialized food manufacturing facilities that run 24/7 to keep up with the chain's global demand. It all starts with bread, the literal backbone of every Subway sandwich. Despite being baked in-store daily, Subway's bread dough is actually produced in massive bakery plants before ever reaching a restaurant. The factories, often contracted to industrial bakers specializing in frozen dough, mix thousands of pounds of dough at a time, using high-speed spiral mixers and automated ingredient feeders that weigh flour, water, sugar, yeast, and conditioners to tight tolerances. Each type of bread, Italian, 9-grain wheat, honey oat, Parmesan oregano, hearty Italian, and more, has its own dough formula. Once mixed, the dough is divided into loaves using volumetric dough dividers that cut by weight, not by length, to ensure uniform baking later. The portions are gently rolled and shaped into long, narrow sticks on molder conveyors, then deposited onto baking trays. These trays pass through a proofing tunnel, a warm, humid chamber where yeast activates and the dough rises to its final size. But they're not baked yet. Instead, the risen loaves are par-baked, partially cooked just enough to set their structure and kill the yeast. This is done in high-capacity convection ovens running at over 400 degrees Fahrenheit. The loaves spend just a few minutes inside before being cooled with filtered air, then flash frozen on a spiral conveyor. The rapid freeze locks in moisture, preserves yeast flavor, and prevents the crust from hardening. These frozen, par-baked loaves are packed into boxes and shipped in temperature-controlled trucks to Subway locations around the world. At the store level, employees complete the baking in small convection ovens, giving the bread its warm, crusty exterior and that signature fresh-baked smell. But the structure, size, and flavor were all engineered weeks earlier in factories running like clockwork. Next up, meats and proteins. Subway's proteins are not sliced fresh in store. Instead, they're manufactured in large-scale food processing plants where uniformity is paramount. Turkey, ham, and roast beef begin as whole muscle cuts, often sourced from partner suppliers, and flash frozen upon arrival. These cuts are trimmed, brined, and then steam cooked or roasted in industrial ovens that hold hundreds of pounds of meat per batch. Brining is done under vacuum pressure to ensure full absorption of salt and flavor throughout the muscle. After cooking, the meats are chilled rapidly in glycol-cooled tunnels and sent through high-speed slicers, which slice each piece to exact thickness tolerances, usually just under 2 mm. The slices are then stacked and portioned mechanically. For instance, every serving of Black Forest ham is 4 slices, and every turkey portion is 6 slices. These are weighed automatically, with robotic hands inserting them into vacuum-sealed pouches. Each pouch contains a precise, ready-to-use portion, reducing prep time in stores and eliminating the chance of over-portioning. Subway's more processed meats, like cold cuts, salami, pepperoni, and bologna, are made through emulsification and casing processes. Raw meats are ground and mixed with spices and curing agents in vacuum blenders, then extruded into sausage casings or molded into loaves. These are cooked, chilled, and sliced with ultra-thin circular blades, moving at high speed before being packaged in airtight stacks. Then there's chicken, which comes in several forms: oven-roasted breast, grilled strips, breaded patties, and shreds for items like the rotisserie-style sandwich. Chicken breasts are tumble marinated in massive drums, where flavor and moisture are distributed through mechanical agitation. Grilled strips are cooked on conveyor belt broilers, where radiant heat and searing rollers cook both sides simultaneously before cutting into uniform strips. The cooked chicken is then chilled and packed into food service bags with oxygen absorbers to extend shelf life. Protein items, like meatballs and steak, are also made off-site. Meatballs are machine-formed, cooked in steam ovens, and flash frozen in their marinara sauce. Steak is pre-cooked, sliced, and frozen in bulk bags, often with added broth or seasoning to enhance juiciness once reheated. Nearly all of these proteins are delivered frozen or refrigerated, depending on local food safety laws and distribution times. Subway stores store them in walk-ins or lowboys, where they're portioned and prepared according to daily demand forecasts. What about vegetables? Most are pre-sliced, bagged, and shipped in cold chains from regional produce hubs. Lettuce arrives shredded. Tomatoes, cucumbers, green peppers and onions are sliced in high-volume produce facilities using industrial slicers that sort by size, color, and ripeness. Carrots are often pre-julienned, olives are pitted and sliced by weight, and pickles come brined and pre-cut. These produce plants, clean, sanitize, and process vegetables in washed zones lined with antimicrobial flooring and ozone-treated water baths. Optical sorters remove subpar pieces before packing. The sliced vegetables are packed in modified atmosphere packaging, MAP, bags, where oxygen levels are replaced with nitrogen and CO2 to slow spoilage. Bags are labelled with time and date stamps and have a strict shelf life, often just 3-5 days. At the store, staff empty these bags into prep bins, which are rotated based on FIFO, first in, first out protocols. While tomatoes and green peppers may be sliced fresh in store in some regions, most of the work has already been done at the factory. Even cheese is precision manufactured. Subway's sliced American and provolone are pre-cut in industrial dairy plants, where large blocks of cheese are sliced using wire cutters or ultrasonic blades, then interleaved with film to prevent sticking. Shredded cheeses like mozzarella or Monterey cheddar are pre-mixed and coated with anti-caking agents before being shipped in sealed bags. Every item is packed to support Subway's global supply chain. Boxes are coded by product, lot number, and production date. QR codes link to supplier details and quality checks. Temperature sensors are built into pallets to detect cold chain failures. Everything from deli meats to banana peppers is logged, scanned, and traceable. Back in the factories, sanitation is near obsessive. All equipment is cleaned in place daily with caustic foaming agents and food-safe steam. Conveyor belts are removable and made from non-porous plastic polymers. Floors are angled for drainage and cleaned hourly. Workers wear full PPE, including gloves, hairnets, beard guards, and gowns. Entry into production zones requires passing through sanitizing air curtains and foot baths. Factory temperatures are tightly controlled. Cold rooms never rise above 41 degrees Fahrenheit. Warm zones like ovens and proofing tunnels are separated by temperature-locking vestibules to prevent microbial crossover. Air is filtered through HEPA systems to remove particulate matter and pathogens. Every food item undergoes microbiological testing, both at the production site and third-party labs. Products are sampled in real time from the line, plated onto culture media, and incubated to check for E. coli, Listeria, or Salmonella. Batches are not released until testing clears. And then there's distribution. Subway partners with a network of food service distributors who move products from regional hubs to stores every 2-3 days. Trucks are loaded using route-optimized software, and each delivery contains just enough to stock the store without overloading fridge space. Bread dough, meats, cheese, sauces, and produce all arrive together, prepped, chilled, and ready for that made-to-order illusion. In truth, the fresh assembly line at Subway is just the final 5% of a process that begins weeks earlier in factories designed for speed, safety, and consistency. Every slice of meat, every loaf of bread, every spoonful of tuna is measured, packaged, tracked, and delivered to make sure that a sandwich made in Omaha tastes exactly like one made in Orlando or Osaka. So while it may seem like your sandwich is made right in front of you, it's really the result of an entire industrial food system humming quietly in the background, mixing dough, slicing tomatoes, marinating chicken, and portioning cheese by the ton. Subway is a global sandwich brand built not just on customization, but on the relentless predictability of factory precision. And every 6-inch sub starts in a facility engineered to make fresh feel effortless.